All right. Welcome to the hard version, which really isn't that much harder than the last considered easy version of limiting reactants. We have an extra step. All right. And it's a step that you're very familiar with. So let's get into it. We're going to read the first part to get our chemical equation because that's the most important thing. Then we can use that to proceed kind of where we need to go. So it says, we need to produce iron 3 chloride to purify our water when stranded on an island. Okay. Lucky for us, we have a rusty car, which has a lot of iron 3 oxide, and a small bottle of hydrochloric acid. All right, so what we're going to do is we're going to first take a look at our reaction. Now, this one reads backwards a little bit. So one of the things it says right away we produce, so Fe plus 3 chlorine minus 1, right? Balance this guy. That gets us our 3. Doesn't really tell us anything else, so let's go back to the other side. And it says we have iron 3 oxide. So let's use that. Iron 3 oxide, so it's EOF, so that's an iron 3 with a plus 3 and a minus 2, so we crisscross to get Fe2O3, okay? Plus, it says we're going to mix that, or we're going to combine that with hydrochloric acid, which is HCl, right? Plus 1, minus 1, don't need to worry about that. So when we look over here, the thing we're missing is the Fe went with the Cl, so the H is going to go with the O, and you could write that as H2O, and you would probably be okay, right? Because that's usually the combination hydrogen as a plus 1 and oxygen as a minus 2 would come in. So it works out in this case, or else I'd give you more information. All right, so we got our chemical equation. Now we got to balance it. So to balance it, I'm looking at 2's and 3's over here, a 3 right there. All right, so I'm going to deal with my Fe first. I'm going to give myself a 2 right there. All right, which gives me 2 irons, great, 6 chlorines. All right, so that probably means I'm going to need a 6 here, but let's check my oxygens first. So over here I need 3, so I'm going to put a 3 right there, which is good. Again, I would need 6 hydrogens, which is awesome because that means I can put a 6 right there and I'm done. Okay, now showing your work on there can be good. You just, but if you can do some of that in your head, you have to show a chemical equation balanced. But I think we're to the point where a few of you, if not all of you, can do that type of stuff in your head. All right. So good to go. So now we have the rest of the question. It says we scraped together 40 grams of iron 3 oxide. So I'm going to write that. I have 40.0 grams right under it, just like we've done the past 2 weeks of iron 3 oxide. And it says we have a 25 gram bottle. 0.0 gram bottle of hydrochloric acid. How much ferric chloride, right? So our unknown is right here. How much ferric chloride can we produce? All right, so just like we worked on before, we can't use both those numbers. We got to figure out, first of all, which one of those runs out in order to do the stoichiometry to get to the conclusion that, hey, I can produce, in a best case scenario, this much FeCl3, that iron 3 chloride. Okay, so doing that, let's take a look at, we'll do our 25.0 grams of HCl. Okay, now I can't compare anything at the gram level. So what I need to do is I need to first convert this to moles. Again, a step that you should be very comfortable with. So 1 mole of HCl is going to be equal to, looking at the periodic table, 36.51 grams of HCl. Okay, and that gets us a 0.684 moles HCl. Good. All right, do the same thing with iron. Okay, so my iron, which is 40.0 grams of Fe2O3, right? Doing the same steps, 1 mole of Fe2O3. And under here, I would have 159.6 grams of Fe2O3. Okay. And for that, I end up with 0.251 moles of Fe2O3. Great. All right, so basically what we just did is we got to where we were at in the easy problem, right? A little bit more work, but it's not something we're unfamiliar with, right? That guy right there, we could consider these our halves, but it's a lot easier to consider the number of moles your halves. So this is what we have, right? That's what we have to work with. We got to figure out which one of those is going to run out first. So what we need to get over here is we need to get, how much we need, or another way to see it, is how much we're going to use up, right? In order to do that, we need to go through and compare moles to moles, right? Just like before. So down here, I'm going to put moles of HCl. I want to get rid of it. And I need to compare that to moles of Fe2O3. Opposite here, moles of HCl on the top versus moles of Fe2O3 on the bottom. All right. And I like doing this just to make sure, everything I need is going to work out. Then I'm going to go back and look at the numbers, right? So I'm using my coefficients out in front. So that is a 1, that is a 6. This is a 6, that's a 1, right? In the end, what I'm going to come up with is over here, this is going to be my moles of Fe2O3. And down here, run out of space, is going to be my moles of HCl. Okay, so what we end up with is 0.114 moles of Fe2O3, and moles of HCl comes out to be 1.50 that we would need. All right, so if we go back to the problem we did before, right? What we're doing is we are comparing what we have to what we would need, what we have to what we would need, right? So the idea is if I use up all of this, so that goes down to a 0, we use up all of it, I would need 1.5 moles of HCl. Do I have 1.5 moles of HCl? I don't, right? I don't have that. If we do it the same way, if I have 0.684 moles of HCl, I would need 0.114 moles of Fe2O3. Do I have 0.114? Yeah, I have plenty. And so what both of those scenarios tell us is this guy, the HCl is the limit, right? And the Fe2O3 is the excess, okay? Depending on how I ask the problems, both of those are usually necessary, okay? But the one that is the most useful, at least right off the bat with a typical problem, is going to be this guy. We need to know the limit, right? We need to know which one runs out first in order to do our stoichiometry. So we'll do the stoichiometry right now. And the idea is you can start here with the 25 grams, or you've already done basically step 1. This would be the same step 1 no matter what. You can start right back here, all right, with the moles of HCl, knowing that this step's going to be first to figure it out, right? So I'll go back and I'll start at the beginning step, but you'll see that it's going to end up being the same thing. But the more rounding we do, the further our answer could be from the truth. And again, on this, the more precise you are, the more points you're going to get, right? So if I have my 25.0 grams of HCl, right? I know that my next step, because that's my limit, right? I need to know that. I know my next step is going to be the exact same one I put up there. So I have my 1 mole of HCl over my 36.51 grams of HCl. Okay. Next step, we are going to go and we are going to do our mole to mole step. So that is going to be 6 moles of HCl. And that is going to be 2 moles of FeCl3. All right, good. And then finally, right, we need to get rid of our moles of FeCl3, remembering not to bring that down. And if we calculate FeCl3, 162.3 grams per mole of FeCl3. Put that all into the calculator, and we should be able to produce 25.0 divided by 36.51 times 2 divided by 6 times 162.3. And we come up with being able to produce 37.0 grams of FeCl3. Okay. Now, again, we could continue this problem. Maybe I said, hey, this is the percent yield problem. That would be our theoretical. And then we can use whatever we actually got in lab and divide the two numbers and come up with an answer. One of the more typical ones on these problems is to solve for the excess. Like, how much stuff did we have left over, right? In order to do that, we don't necessarily need this number unless we want to go back and calculate how many grams was left over. We have the information right here. So if we take how many moles, 0.251 moles of Fe2O3 we had, right? And we subtract how many moles we use, so it's 0.114 moles of Fe2O3 we used, right? We come up with 0.137 moles of Fe2O3. Now, if we want to convert that to grams, then we can just take that 0.137 moles of Fe2O3, and I would do this as one long problem, except for I ran out of space, and do the molar mass, so 1 mole of Fe2O3 over, let's see, what was my grams of Fe2O3? It's up there. So 159.6 grams of Fe2O3. And then I come up with a mass of, let me check that out, 0.137 times 159.6, right? So we would have had, out of our 25 grams, we would have had 21.9 grams of Fe2O3 left over. Okay, so basically what we're saying is our reaction wasn't very stoichiometric because we have a ton of this left over. We really could have made a lot more water. We could have made a lot more FeCl3, right, to purify water if we would have had more hydrochloric acid. All right, good luck. Have fun. Stay safe.